Okay, here we go. Um, just like we did with addition and subtraction, we're going to start out talking about these properties that go along with multiplication. Same properties we've seen before. Commutative, that is about order. Associative, that's about grouping, not about parentheses, it's about grouping. And identity, but remember, to have an identity property, it has to work in both directions. To start out with just an example of commutative of multiplication, if we wanted to do 4 times 6, would that be the same as 6 times 4? And sure enough, it would. Those are both 24. You're probably pretty comfortable with the idea that we can multiply numbers in any order we want to. So the commutative property does work for multiplication. And if we wanted to write this in a more general format, we might just say that A times B is equal to B times A. We can use numbers as examples. That's really helpful for us to sort of put it in place. But if we want to fine tune it a little, make it a little more abstract, we can write it that way. Associative, that's about grouping. And so an example might be 2 times 3 times 5 is 2 times 3 times 5. Well, I'm not positive about this one. Commutative, I was pretty comfortable with right out of the gate. This one, well, let's see if this one works. 2 times 3 would be 6 times 5, which would be 30. And this would be, do the parentheses first. This would be 2 times 15. Sure enough, that's 30. What you're going to find as you do these over and over, different numbers, you're going to find that the associative property does work for multiplication. So we do have a commutative property of multiplication. We do have an associative property of multiplication. And what the associative could look like is A times B times C is equal to A times B times C. That would be the abstract way of writing that out without putting actual numbers in. If you have any questions about these, make sure you let me know. Commutative and associative do work for multiplication. Identity. Let's see, is there a number I could multiply something by and get that same number back? Normally I'd wait for you to type it in, but since we're doing 2 sections today, I'm going to roll right into it. That would be 1. And 5 times 1, sure enough, would give us 5. So there is a thing out there we could multiply by to get the value right back. We would call one the identity element. You're not going to be asked about that. It's just sort of informational. And in order for this property to hold, this has to work both ways. I have to be able to do 1 times 5 and get 5. Okay, I do. So sure enough, yes, we have an identity property of multiplication, and that would just look like A times 1 is equal to A. So commutative and associative and identity do work for multiplication. Let me know if you have any questions about that before we go on. Okay. Some other properties that deal with, or that are related to multiplication. Whenever we multiply by 0, we get 0. And that could be if it's 2 times 0, we get 0. If it's 0 times 2, we get 0. Either way, anytime we multiply by 0, we get 0 back. And so we have a 0 property of multiplication, that is A times 0 is going to equal 0. Anything we multiply by 0 is going to give us 0 back. Distributive, and this is more of a reminder, it's just something that sort of relates multiplication and addition or subtraction together depending on what you've been given. But if we have something like 7 times x plus 3 and we want to get rid of those parentheses, we want to simplify this. The way that gets done is this 7 is being multiplied by everything in those parentheses. It's getting distributed through the parentheses. And so when we multiply here, we end up with 7 times x plus 7 times 3, 7x plus 21. Sort of a abstract general way to write the distributive property is that A times B plus C is equal to AB plus AC. We distribute the A through the parentheses, meaning we multiply the A by everything that's inside those parentheses. Let me know if you have questions on any of that before I give you a question to answer. Okay. Closure. Remember, closure is the idea that is if I do something with numbers from a given set, is the result also in that set? And my question to you is a true or false one. I'll make a poll for this. The set of integers is closed under multiplication. So the idea here is if we multiply two integers together, do we get an integer as our answer? For it to be true, it has to be true all the time. If you can find one counterexample, one time where this doesn't work, then you can say false. In this particular case, if we multiply two integers, do we get an integer back as our answer? Go another 15 seconds on this, and then we'll talk about it. All right, let's see how we did here. Unanimous. Outstanding. Very good. Okay, great. We'll talk about it anyway, but just to sort of make sure, what I want to do here is I want to try to show this is false. I want to try to come up with a counterexample that makes this false. And if I do that, I want to look at sort of weird stuff. Like if I do -4 times 0, those are both integers, and that's weird stuff. Well, I get 0. That's an integer, so that's okay. And if I did like -3 times -6, well, that's -18. Yeah, it's negative, but it's still an integer. No matter what I try, I'm always going to get an integer back. So sure enough, you're exactly right. This one's true. Multiplication is closed, but for the set of integers. After we did properties and after we did closure, we would look at our standard algorithms. And the first thing I want to do is just kind of run through the standard algorithm for multiplication with 217 times 28. And so this will look very familiar for you. I don't think you'll see anything in here that's a big surprise, but our standard algorithm for multiplying 217 times 28. We'll start out in the ones column and have 8 times 7, and that's 56. We'll put a 6 here. We'll put a 5 up there. And then 8 times 1 is 8, plus 5 is 13. We'll put a 1 over there. And then 8 times 2 is 16, and 1 makes 17. And we just write that down because there's no more columns to carry it over to. If you see something that looks strange or doesn't make sense, you let me know. Then we move over, and here we have 2 times 7, keeping in mind that this is in the tens place. So really what we're multiplying here is 20 times 7. And when we do 2 times 7, we get 14, and we're putting a 4 here, and we're putting a 1 up top in this column. But one of the things I want to emphasize here briefly, and we'll get back to it, we're going to talk a lot more about this after we finish it, is the reason that this 4 goes in the tens column is because of what we're actually multiplying here. Yes, we're doing 2 times 7 so we can do it in our head to get the 14. But really, because this 2 is in the tens column, what we're actually multiplying here is 20 times 7. And 20 times 7 is 140, which is 100 and 4 tens. And so those 4 tens go in the tens column of our answer. All right, continuing through it. Now we've got 2 times 1 is 2, plus 1 is 3. Notice those go in the hundreds place. 2 times 2 is 4, and then we can add these together. And when we add, we'll end up with, let's see, a 6. 3 and 4 is 7. 7 and 3 is 10. I'll carry a 1 over and get 6,076. Just for the standard algorithm part, let me know if there's anything in there that you want to ask about before we sort of investigate this in a lot more detail. All right. Emphasizing those place values is something I want to do here. I want to really sort of um, really get into those place value positions. And what I mean by that is when we multiply this 8 times this 7, what we're really multiplying there is pretty straightforward. That's just 8 times 7. It gives us 56, which is 5 tens and 6 ones. And so that's what we need to do in our problem. And you'll notice we put these 6 ones in the ones column. We put those 5 tens in the tens column. So that's what's actually happening there is 8 times 7. That one's not necessarily that um, interesting, but what happens in the next one is here we have this 8 times this 1. And yeah, when we're working through it, we think of it as 8 times 1, so we can do it in our head. But really what's being multiplied there is that's 8 times 8 ones times 110. 8 times 10 is really what's happening there when we multiply those. And so we have 8 times 10. And then on top of that, this 5 tens that we carried over from last time, when we did 8 times 7 to get 56, we're adding that in. So we're doing this 8 times 10, and we're adding those 5 tens in. So we have 8 times 10, which is 80, and then we're adding 50 on top of it, and the result of that is 130. And I want you to see what happens in the problem. We wind up with a 3 in the tens place, and we carry this 1 over to the hundreds place because it's 130. That's what we got when we multiplied there. Yes, I want to make sure that you can multiply using the standard algorithm, but I also want to take a little time and investigate each individual step and what's exactly happening there. Continuing this along, when we do this 8 times 2, it's not really 8 times 2. Really, that's 8 times 200, which is 1,600. But then we also have this 100 up here we need to add on, and we do that. And so we get 1,700. And that's what we have right here is this 1,300 or 1,736. Just a reminder of what we're multiplying each step along the way. And I'm going to get rid of some of this over here on the right because I want to emphasize what we're getting when we just do the multiplying. When we just do the multiplying, yes, we're adding that extra step on, but questions that your book likes to ask that I follow along with is what is it that we're multiplying here in this step? And when we do that when we do this 8 times this 1, we're actually multiplying 8 times 10 because it's in the tens place. When we do this 8 times 2, we're actually doing 8 times 200 because that 2 is in the hundreds place. And then what we see here, when we multiply 8 times 217, the result is 1,736. That's what the 1,736 represents. Continuing down a little bit, when we multiply this 2 by this 7, what we're actually multiplying there is 20 times 7, and that's 140. When we move over and do this 20 times this 10, we're really multiplying 20 times 10 there, and that's going to be 200. And then when we do this 20 times this 200, that gives us 4,000. And then you'll notice what we end up with down here, all we see is 434. But the reason we've bumped over a place value is because we started in the tens. Everything gets multiplied by 10, so we're not going to have any ones here. 4,340 is the result of multiplying 20 times 217. I'm guessing that the standard algorithm for multiplication is very straightforward for you. Thinking about it in these terms, though, is a little bit different than something you may have done before. So let me know if you have any questions about what's going on over here. The types of questions you might see are related to when we do this 8 times this 1, we're actually doing 8 times 10. When we do this 8 times this 2, we're actually doing 8 times 200. When we see this 1,736 down here, what that shows us is the result of multiplying 8 times 217. If that makes sense, then I think you're in good shape, but let me know if you have any questions. Okay, fantastic. Partial products is an alternative algorithm for multiplication. Just like we did with addition and subtraction, we're going to look at the standard way, but then we're also going to look at some other ways. Partial products is a way to multiply, and we just break this down into pieces. If we want to do 217 times 28, and we're going to multiply this using partial products, what we do here is we do each product by itself. So I start out by doing just 8 times 7, and that gives me 56. And so I just write down 56. Then I go over and I do, well, this is 8 times 10. When I do that 8 times 10, that's 80. Then I do this 8 times 200, and that's 1,600. And I just write down each of those partial products as I go. This is a really great way to help students who might be struggling with place value and what it is that everything means in this multiplication setup. Then we go over to the 2, and now we're doing 20 times 7. Let's see, 20 times 7, that's 140. Then 20 times 10 is 200. And then 20 times 200, that's 4,000. And then to finish this off, we just add all those together. This is called partial products. We have each one of those individual partial products, and then we add them together. 56 plus 80 plus 1,600 plus 140 plus 200 plus 4,000. On the calculator, I get 6,076. I could have also done this by hand and just added down this column and got a 6. 5 and 8 is 13, and 4 would be 17. 1 and 6 is 7, 8, 9, 10. Do that. 6,076. Either way, 6,076. Same answer we got this way. It better be, because we did the same problem, 217 times 28. That's partial products, where we just do each little piece by itself. Let me know if you have any questions on that. Okay. The next alternative algorithm we're going to look at is called lattice multiplication. We did lattice addition last week, and this is going to work under a very similar format. We're going to make a box, and we're going to divide that box up into different pieces. Here we want to multiply 217 by 28. So I need 3 place value positions here for my 217. And with lattice multiplication, I'm going to divide this the other way and put the 28 over here. So there's my 217 and my 28. I'm going to do the exact same thing I did with the lattice addition, where I cut that off and extend it down. I chop that diagonally, and chop that one diagonally. Now we're going to go do our multiplications one at a time. A lot of Math 122 students really like lattice multiplication. It emphasizes place value. It puts things where they're supposed to go really nicely without the carrying to the top of the next column that our standard algorithm gives us. We're going to do each one of these pieces and multiply them through. So I'll start out with 8 times 7, that's 56. 8 times 1 is 8, so that's just an 8 in the lower box. 8 times 2 is 16, so I'll put that in there as 16. Then we'll do the same thing across the top. 2 times 7 is 14. 2 times 1 is just a 2, and 2 times 2 is 4. Now it becomes a lattice addition problem where we're going to add along those diagonals. And when I add along those diagonals, what happens is here I have a 6. Here I have 4 and 5 is 9 and 8. That's 17. How am I supposed to carry that over? Just what your instinct would tell you is exactly what you should do. You write the 7 down and you carry the 1 over to the next column. And then 1, 2, 3, 4, and 6 is 10. Write the 0 down, carry the 1 over to the next column. 1, 4 is 5, and 1 is 6. Sure enough, 6,076. We keep getting that same correct answer. That's lattice multiplication, where we basically, what we're doing here is we're doing each individual piece one at a time, and then we go back through and add them. Oh, good. Laura likes this one. A lot of students really like this one. I think it's pretty great. Yeah. Yeah. All right. I'm going to have you practice one like this. So I want you to try 35 times 17. And just to make sure you get a little bit of a push in the right direction, we just need two columns for the 35, two columns for the 17, and then I'll let you finish it from there. With the practice, I might not give you as much time as I would otherwise if we were doing just one section today. So if I start this before you're absolutely ready for me, I apologize. You just keep going, finish it, and then as we go through it, you just look at yours and look at ours and make sure that they match and ask whatever questions you have. Okay, so what I need to do with this lattice is I need to put my lines in here. And you don't have to make those dotted lines. If you just want to draw them all the way, that's fine. There's nothing magical about the dotted lines. Um, and so as we go to do our multiplication here, we'll have 7 times 5, that's 35. Kind of nice. It puts the 3 in the tens column for you automatically. And you can do these boxes in whatever order. It really doesn't matter. If I go up now and do 1 times 5, I put a 5 here. And then when I do 7 times 3, I get 21. And 1 times 3, I get 3. And now I just need to add along those diagonals. And here we'll have 5. 5, 6, 7, 8, and 1 is 9. 3 and 2 is 5, and that's 595. And you can check that. Do 35 times 17 on the calculator. Make sure you get 595, but you will. And that's lattice multiplication. It's a pretty cool technique. I thought I would skip this because of time, but I don't want to. I want to go ahead and show it to you anyway. I'll just do it relatively quickly. Napier's bones, because they were originally made out of bones, are also known as Napier's rods. And what these are is, it was the early 1600s, Scottish mathematician John Napier created the world's first calculator. Napier's rods work using lattice multiplication. Lattice multiplication, really common toward the end of the Middle Ages and then a little bit thereafter. And so what Napier did was he made these basically multiplication tables. If you look at them, if you look here, you've got your ones, which is 1, 2, 3. Your twos, you're multiplying by this index. So 2 times 2 gives you 2. 2 times 7 gives you this 14 down here. In your fives, 5 times 8 would give you 40. And these are just already created. You'd buy a set of these. That I'm not exactly sure where, but you could buy a set of these and you would have these numbers on these rods. And they were originally made out of bones, but they don't have to be made out of bones. They can be made out of rods. And the way that they work is like this. If you wanted to multiply 3 times 76, and this is a really simple example, it would work with anything. But what you would do is you would use your index. Since you're multiplying by 76, you would take your 7 rod and your 6 rod and put those next to each other. And then when you want to do 3 times 76, you just kind of look, okay, here's my 3 row, and I look at the 7 and the 6's put together. And when I look at those, it gives me the multiplication tables right there, and I just need to add now. There's an 8 in the ones column. 1 and 1 makes 2. 2 makes a 2. And so I can look at a quick glance at this and see that 3 times 76 is 228, because I see 228 right there in the rods. And it absolutely works. They're pretty neat. And the only other thing I wanted to show you about this is if you wanted to do these with students, large popsicle sticks make for a great way to make Napier's rods that you could use with your students. If you want to do lattice multiplication, just to kind of show them this cool thing, I think that's worth it. It's kind of wild that in the 1600s, this was used as sort of the first ever calculator. I'm not going to ask any questions about Napier's rods, Napier's bones. I just wanted to let you know they exist and they go with lattice multiplication. Okay. I didn't want to spend too much time on it because we have to do 2 sections today. The next alternative method for multiplication we're going to look at was done by the Egyptians, and it's called Egyptian duplation. What we do in Egyptian duplation is we have 2 numbers, and we're going to double one of those numbers and keep track of how many we have. My general advice, it's not a hard, fast rule, but the problem goes a little faster if you double the larger number. And you'll see why as we do this. So what I mean by double and keep track is we've got 35 and I have one of them so far. I'm going to double that to 70. And now I have 2 35s. What I'm doing in my keep track column is I'm keeping track of how many 35s I have. When I double this again, now I have 140, and in there I have 4 35s. Again, the keep track column is just keeping track of how many 35s are in there. If this is not making sense, you tell me and we'll talk about it. The idea is we take one of those numbers and we double it, and we keep track of how many we have over on the right. Where we're headed with this is right now I have 4, 5, 6, 7 35s all together over there. Well, eventually I need to have 11. So I need to keep going with my doubling. So I'm going to double again, and that'll be 280. And then that's 8 35s in there. And now what I want to do is I want to do 35 times 11. Well, let's see what I should keep over here. If I keep this number, that's 8 35s. If I keep this number, that's 2 more 35s. So now I'm up to 10. And if I keep this one, that's 1 more 35, and I'm up to 11. And so what we're going to do is we're going to add those circled numbers together, because this gives me 1 35 plus 2 more 35s plus 8 more 35s. And we'll add those 3 together. And let's see, that'll be a 5. 3 and 7 is 10, and 8 is 18, and 385. And then we can check just to make sure, in case you're a little skeptical. 35 times 11, sure enough, 385. That's Egyptian duplation. Keep in mind that if you are an Egyptian doing this, I'm not going to ask you to, but if you're an Egyptian doing this, one of the reasons this works so well is the number 35 for an Egyptian. To double it just means make twice as many of those symbols. So when I go from 35 to 70, I just go from there to 70. And then I want 140. And so doubling was something that wasn't very hard to do in their number system, and then you just had to go back and add them together. It's an additive system, so it's pretty easy to keep track of. I want you to try one using Egyptian duplation. I'm not going to make a poll, but I'll just give you a minute to try to practice. 27 times 9. Again, my advice is to double the 27, because you go until you have 9 of them and then you can quit. That's the advantage to doubling a larger number. Otherwise, you'd have to double 9 all the way until you had 27 of them. So that would take longer. And just like the other one, I'll give you a chance to go through it. I might start faster than you want me to, but hopefully not too much faster than you wanted me to. If I have 27, that's one of them. I'll double that and have 2 of them. I'll double that and have 4 of them. It's 4, 5, 6, 7. I'm still not quite there, so I'll double it again. 216, that's 8 of them. What I want is I want to have 9 27s in here. And so I'm going to use 8 plus 1 more. I'm going to add those 2 numbers together. And 7 and 6 is 13. 1, 2, 3, 4, and just a 2. So 243 is what I get when I multiply 27 times 9. Let me know if you have questions about that. And one of the things I want to show is that this really emphasizes that it's a beautiful example of the distributive property, because how we got to 243 here is we did 27 times 1 plus 8. We did 27 times 1 plus 27 times 8. That's how we got to 243. The Egyptian duplation is a beautiful example of the distributive property. We just kind of have to think about it in those terms, that what we did was 27 times 1 plus 27 times 8. Let me know if you have any questions on that. Okay. One more method, probably the most strange of the methods. It's called the Russian peasant method. It was very prevalent in the Middle Ages. In this method, instead of double and keep track, what we're going to do is we're going to have one of the numbers and double the other one. My advice here is to have the smaller number because it makes it go faster. So let's look at 27 times 51 using what's called the Russian peasant method. So I start out with 27 times 51, and I'm going to have the smaller number and double the larger number. So when we have, we're going to drop any fractional part. Basically drop any remainder, drop any fractional part, because it's going to happen right away in this one. When I have 27, I'm going to get 13.5. We just drop the 0.5 and call it 13. Going along with this, I'm going to double that 51 and have 102. I'm going to have again 13, that'd be 6.5. Drop the 0.5 and keep the 6. Double that to 204. Half that, and it becomes a 3. Double that, it's 408. Half that, it becomes 1.5. Drop that 0.5, it's a 1. Double this again, it's 816. So far, so good, probably. This is the part that gets interesting. What we are going to do is we are going to look in the halves column, and we're going to keep anything that has an odd number. So anything that has an odd number in the halves column, we're going to keep that. So we're going to keep the 27, which means we want the 51, really. That's an odd number, so we're keeping the 102. That's even. That's an odd number, so we're keeping 408. That's an odd number, so we're keeping 816. And now, just like we did with Egyptian duplation, we're going to add all those four together. So we'll wind up with 51 plus 102 plus 408 plus 816 is 1,377. And you could try it. 27 times 51, sure enough, ends up at 1,377. What is happening here, the reason that we keep the odd numbers is because we're dropping that fractional part. When we drop this fractional part, we lose some of the number. So if this would have just been 13.5 times 102, we would have still had the same problem that we started with. When we drop that half, that's why we have to keep that number. Anytime we drop down, when we drop down from 13 to 6, we drop that 0.5, that's when we need to know we need to keep this number. Here, 6 times 204 and 3 times 408, those are exactly the same as each other. It's when we have to drop that half that we have to keep the number, and so it's when we have an odd number, we keep the one in the doubles. I'd go into more detail on this if I had more time, but I don't. If we want to talk about it more on Monday of next week, I'd be happy to. Okay, I want you to try a Russian peasant method and see if you can do it. 27 times 9, have and double. My recommendation is that you have the smaller number because you'll get to 1 faster that way. Have the smaller number. Keep the odd numbers in the half column. and add the numbers in the doubles column. Of the alternative algorithms for multiplication, I think this is really interesting that it was the way to multiply in the Middle Ages. I think Egyptian duplicity is kind of cool because it's distributive property, but the one that's the most practical is the lattice. That, my opinion. You may feel differently. If we're going to have and double here, and I have 27 times 9, and I'm going to have the 9 and double the 27. Okay, so I'm going to double this to 54. I cut that in half. It becomes 4.5, so it's just 4. Then I need to half again. It's 2, and that's doubled to 108. And I half again to 1, and that's 216. And when I look at this, let's see here. I want to keep the odd numbers in the halves. Those are the doubles I'm going to add together. Keep the odd numbers in the halves. Those are the doubles I'm going to add together. And you'll notice we'll do 27 plus 216. And we get 243. One thing I want to do here is I want you to notice that the Russian peasant method, 27 times 9, gave us 243 because we added the 27 and the 216 together. When we did Egyptian duplicity with 27 times 9, we got 243 because we added the 27 and the 216 together. The Russian peasant method isn't exactly the distributive property, but it plays out in a very similar way. Make sure you know the difference between those two methods. Egyptian duplicity, we have and keep, or excuse me, we double and keep track. Russian peasant, we have and double. A little bit of mental multiplication before we put multiplication away. It's possible there's other ways to go about multiplying mentally, but as just sort of a blanket, straightforward, relatively simple way to go, if we can change the numbers to make them easier to multiply, that's a great thing. And when I look at this, I think multiples of 10, multiples of 100, that would be really nice. 64 times 5, I can't really do that in my head, but I could double this number and make it 10. And it doesn't change the problem if I were to cut this one in half and make it 32. What we're saying here is that 64 times 5 is the same thing as 32 times 10 because I doubled one of the numbers and I have the other one. Not necessarily about having and doubling, as you'll see in some future examples, but 32 times 10 is the same as 64 times 5, and 32 times 10 I can do in my head. And so if I wanted to multiply 64 times 5 mentally, I could change it to 32 times 10 and know that it's 320. Look at a couple of other ones. 16 times 25. Gosh, I'm not seeing a whole lot in there I could do. Wait a minute. I could turn this 25 into 100 if I multiply it by 4. But to keep the value of the problem the same, if I multiply that by 4, I need to divide this by 4. And 16 times 25, well, that's really just the same as 4 times 100, which I can absolutely do in my head. The idea behind these that we are going to use is trying to get to multiples of 10 or 100, because that's a relatively simple way to go. The one on the right, there's two obvious paths you can take here. I kind of feel like if I take 60 and I multiply by 10 to get 600, and I take the 30 and divide by 10 to get 3, now I can do that in my head. 600 times 3 is 1800. By multiplying one of the numbers by something and dividing the other one by the same thing, we've created a new problem that is exactly the same as the old problem. Let me know if you have any questions on that. Okay. Last thing is estimation, and this is just one approach to estimation with multiplying, but it's a way that allows us to do it mentally. Remember, an estimate, we're not looking for an exact answer. We're looking for something in the ballpark. we probably don't want to drop that 78 down to 70 and drop the 52 down to 50. Instead, what we'll do is we'll bump one of these up and the other one down. And now it's 80 times 50. And just like we saw a minute ago, well, then I can make this 800 times 5, and then I can turn that into 4,000. Just an estimate. We don't expect it to be exactly right, but by making one of the numbers a little bigger and the other one a little lower, that's going to give me a better estimate than if I make them both bigger or if I make them both lower. All right. Let me know if you have any questions on that before